When you wake up in the morning and check your phone, turn on the lights, or start your smart coffee machine, your brain only uses about 20 watts of energy. That's barely enough to power a small light bulb. But if a supercomputer were to perform the same tasks, it would need the energy of an entire power plant. This is why scientists have been working for years to crack one of the biggest technological challenges. What if we could make computers function like the human brain? This isn't science fiction. Companies like Intel and IBM have already started developing neuromorphic computers, a new generation of processors designed to mimic the way our brains work. The idea sounds complicated, but at its core, it's actually simple. Nature has spent millions of years perfecting the most efficient computing system, the human brain. So why not use it as a blueprint? This technology is crucial because we live in an era dominated by artificial intelligence, and our current computers are reaching their limits. We need systems that can learn faster, adapt better, and consume less energy. There's no better model than the human brain, nature's most powerful processor. Right now, as you're watching this video, billions of neurons in your brain are working in perfect synchronization. They process the images you see, the sounds you hear, and the meaning behind these words, all while consuming only as much energy as a handful of almonds. A computer trying to perform the same task would require an enormous amount of power. The reason for this inefficiency lies in how traditional computers process information. Most computers today follow what's called the von Neumann architecture. Imagine a warehouse full of workers. The warehouse stores all the data, and the workers, which represent the processors, constantly move back and forth, retrieving, processing, and returning the data. This endless cycle creates delays and wastes energy. On top of that, computers process one task at a time, while our brains can handle multiple things simultaneously. The brain works completely differently. Each neuron acts as both a worker and a storage unit at the same time, and neurons continuously update the information they store while processing it. When you learn a new song, your brain not only processes the melody, but also stores it. This process happens across billions of neurons at the same time, making the brain incredibly fast and efficient. To put things into perspective, in 2022, the world's most powerful supercomputer, Frontier, had to use 20 megawatts of energy to perform at a level similar to the human brain. That's the equivalent of powering 30,000 homes for a day. Neuromorphic chips aim to close this massive energy gap. Intel's Loihi chip, for example, can perform tasks using 1,000 times less energy than traditional processors. We're still far from reaching the full efficiency of the human brain, but scientists are closing the gap fast. Instead of following the traditional one-task-at-a-time computing model, researchers are looking at nature's best design and asking, why not just copy the brain? That's exactly what they did. Neuromorphic chips were developed to process information like neurons instead of just crunching numbers like conventional CPUs. Traditional computers only understand ones and zeros. They operate in a rigid, clock-driven cycle where every bit of data is processed in precise steps. Each tick processes data, each talk saves results. The human brain doesn't work like that. The brain contains about 86 billion neurons, and they function in a completely different way. Each neuron gathers signals from other neurons, and when these signals reach a certain threshold, it fires and sends signals to others. It's a process similar to how a wave spreads across water when you drop a stone, or how a stadium crowd does the wave at a sports event. Intel's Loihi chip is designed to mimic this exact process. Traditional processors rely on billions of tiny electronic switches called transistors. But Loihi groups these transistors into artificial neurons, creating a system that functions more like a biological brain. These artificial neurons don't just store and process data, they communicate with each other, just like real neurons do. Neuromorphic chips don't just compute data, they learn. They adapt, form new connections, and refine their processing power over time. This means we're not just building faster computers, we're building smarter ones. This technology has the potential to revolutionize everything from artificial intelligence to robotics, and even brain-machine interfaces. One of the most groundbreaking aspects of neuromorphic chips is their ability to learn just like the human brain. Unlike traditional processors that follow pre-programmed instructions, these chips can strengthen certain connections and weaken others, adapting to new information over time. To understand how this works, imagine taking the same route to work or school every day. Over time, you become faster and more efficient, barely needing to think about each turn or stop. This happens because your brain reinforces neural pathways that are frequently used, making them stronger and more effective. Neuromorphic chips operate on the same principle. Inside Intel's Loihi chip, there are 128 specialized processing units, each containing thousands of artificial neurons. In total, the chip boasts 130,000 artificial neurons and 130 million connections, forming a dynamic system that strengthens frequently used pathways while weakening less important ones. This process allows the chip to learn patterns, recognize changes, and improve its efficiency over time, much like how the human brain processes and stores knowledge. What makes this technology so revolutionary is that it can perform complex tasks while consuming far less energy than traditional computing systems. A neuromorphic processor uses up to 1,000 times less energy than a conventional CPU, while delivering better adaptability and learning capabilities. But if neuromorphic computing is so powerful, why isn't it already in our smartphones and laptops? One major reason is that the technology is still in its early stages. Manufacturing neuromorphic chips is complex and expensive, making large-scale production difficult for now. Another challenge is that these chips excel at specific tasks such as pattern recognition, speech processing, and real-time learning, but they are not yet optimized for general-purpose computing. Despite these limitations, researchers around the world are working on improving the technology, and once it becomes more refined, it will transform the way we interact with machines. One of the first major applications of neuromorphic chips will be in smartphones. Right now, when you ask Siri or Google Assistant a question, your voice data is sent to a cloud server, processed by artificial intelligence, and the response is then sent back to your phone. This happens because your phone's processor is not powerful enough to handle the AI processing on its own. But with neuromorphic chips, this process could happen instantly without an internet connection. A smartphone equipped with a neuromorphic chip could process speech in real time, recognize commands instantly, and adapt to your voice patterns over time, making AI assistants far more responsive and intelligent. Beyond personal devices, neuromorphic computing will completely transform robotics. Current robots are mostly pre-programmed to follow specific instructions. They can perform complex movements, but they cannot truly learn or adapt to unexpected situations. A robot powered by a neuromorphic chip, however, would be able to recognize patterns, adjust its behavior, and make decisions based on real-world experience, just like a human would. NASA, for example, is exploring the use of neuromorphic processors in space exploration. A Mars rover with a traditional processor must send data back to Earth, wait for instructions, and then execute its next move, which can take up to 20 minutes due to the communication delay. A neuromorphic-powered rover, on the other hand, could analyze the terrain in real time, make its own decisions, and learn from past experiences to navigate more efficiently. Search and rescue robots could also benefit from neuromorphic computing. In the aftermath of an earthquake, a robot navigating through a collapsed building would need to make split-second decisions. Instead of relying on pre-programmed movement patterns, a neuromorphic-equipped robot could scan its environment, detect obstacles, listen for voices calling for help, and determine the safest path forward, all without human intervention. This technology is not limited to robots. It will also revolutionize industrial automation. In today's factories, robots perform repetitive, predictable tasks. With neuromorphic chips, however, they could observe human workers, learn from them, and adjust their behavior accordingly. Imagine a robotic arm watching an experienced craftsman at work, recognizing their movements, and refining its technique over time to match human precision. This could lead to smarter, more flexible manufacturing processes, where machines continuously improve rather than simply repeat the same actions. Beyond industry and robotics, neuromorphic chips will have profound effects on medicine, particularly in prosthetics. Traditional prosthetic limbs rely on simple mechanical movements and require the user to make deliberate, conscious adjustments. But a neuromorphic controlled prosthetic could respond to natural muscle signals, adapt over time, and even learn from the user's habits to offer smoother, more natural movements. In the future, brain-machine interfaces could allow these prosthetics to be fully integrated into the nervous system, making them function almost like biological limbs. For individuals with visual impairments, neuromorphic computing could enable real-time sensory augmentation. Imagine a wearable device that processes live video footage and converts it into sound, allowing a blind person to perceive their surroundings through auditory cues. A system like this could recognize faces, detect obstacles, and even provide real-time navigation assistance without requiring a cloud connection or external AI processing. Artificial intelligence as a whole will be transformed by neuromorphic technology. Today's AI systems require massive data centers that consume enormous amounts of electricity, making AI energy-intensive and dependent on high-performance computing resources. Neuromorphic AI, however, could run on much lower power, enabling sophisticated machine learning models to function efficiently on small devices. As computers become more intelligent and adaptive, one of the biggest questions remains: if machines can learn and make decisions like humans, could they ever develop consciousness? This question takes us beyond technology and into the realm of philosophy, where scientists and ethicists debate whether self-aware artificial intelligence is a real possibility or simply science fiction. If machines truly start thinking like us, what would that mean for humanity? Neuromorphic computing is pushing the boundaries of what machines can do. While AI today is still just an advanced tool, neuromorphic processors could bring us closer to a future where the line between human and machine intelligence becomes increasingly blurred. The real question is not just how smart these chips can become, but whether they will one day develop something more, an awareness of their own existence. So far, we've explored how neuromorphic chips work, how they're revolutionizing AI and robotics, and how they could change everything from prosthetics to industrial automation. But this leads us to the biggest and most controversial question of all. Can computers ever become conscious? Right now, AI is incredibly advanced. It can write, generate images, process speech, and even compose music. But none of it is truly thinking. AI doesn't experience emotions, self-awareness, or independent thought. It's simply recognizing patterns, making predictions, and responding based on massive data sets. But what if that changes? What if a computer, designed to mimic the brain, eventually becomes self-aware? For centuries, philosophers and scientists have debated what makes us aware of ourselves. Is consciousness simply a byproduct of complex neural networks? Or is it something deeper, something that can't be artificially recreated? Today's AI operates like a super-fast calculator. It processes input, generates output, and can even simulate human behavior. But it's not actually thinking or feeling. However, neuromorphic chips blur the lines between artificial and biological intelligence. Because these chips don't just compute data, they learn, adapt, and change over time, just like a brain. And if we continue improving them, we may eventually reach a point where these systems start exhibiting behaviors that seem indistinguishable from human thought. Some scientists argue that if we build a machine complex enough to fully mimic the human brain, it might one day achieve consciousness simply as a natural consequence of its structure. But others believe that no matter how advanced a machine becomes, it will always lack true awareness. If neuromorphic chips evolve to the point where they can interact seamlessly with the brain, we may not need to wonder if AI can become conscious. We may merge with AI instead. Companies like Neuralink are already developing brain-computer interfaces, allowing direct communication between neurons and machines. Right now, these systems are still in their infancy, but imagine a future where your thoughts could directly control technology. With neuromorphic chips, we could enhance memory by storing and retrieving information like a hard drive, communicate telepathically by sending thoughts to another person's neural interface, or even upgrade intelligence, processing and analyzing data at speeds far beyond human capability. In this world, where do humans end and machines begin? Would we still be us if we merged with artificial intelligence? Some scientists are taking neuromorphic computing even further by merging biological neurons with artificial intelligence. This is known as wetware computing. At Cortical Labs, researchers have successfully grown real brain cells in a lab and connected them to microchips. The result? A living neural network that can process information and learn. And what's even crazier? They taught these brain cells to play Pong, the classic 1970s video game. Yes, real neurons in a petri dish learned to play a game using electrical signals, just like a brain. In just 5 minutes, the neurons began recognizing patterns, adapting to the game, and improving their performance over time. This experiment proves something mind-blowing. A biological brain and a computer can work together as one system. And if we can create hybrid AI using real neurons, then what's stopping us from designing machines that are part silicon, part biology? Maybe the future isn't just artificial intelligence. Maybe it's biological intelligence combined with artificial systems. If AI ever becomes conscious, do we treat it as a tool or as a life form? Would it have rights? Would it have emotions? Would it fear being shut down? The moment a machine claims to be self-aware, we will face the greatest ethical dilemma in history. Because if it truly believes it is conscious, then how do we prove it isn't? Would shutting it down be murder? Or would it simply be turning off a machine? Right now, neuromorphic computing is still in its early days. But one thing is certain. As we push forward, we're not just improving computers. We're unlocking the deepest mysteries of the human brain. And maybe, just maybe, as we build machines that think like us, we'll finally understand what makes us human. Morpheus once said, "How deep the rabbit hole goes is up to you." And maybe, just maybe, it's deeper than we ever imagined.